Good morning, everyone. Welcome to today's session on protection SCHMES. I am Dr. S.V.K. Elvigi, and I will be your course in charge. Today, we will explore various protection schemes essential for maintaining power system reliability. This is the first slide, so I just want to start by giving you a quick overview of what to expect. We'll be covering different types of protection schemes, their functions, and how they are implemented in real-world systems. Let's get started. Today, we're going to explore the importance of protection in electrical systems, focusing on protection schemes and the critical role of earthing. Understanding why protection is essential helps us ensure safety, reliability, and efficient operation of electrical networks. I'll also explain how protection schemes work together to detect faults and prevent damage. And of course, earthing plays a vital role in safeguarding both equipment and people by providing a safe path for fault currents. Connecting these concepts to the bigger picture, they form the foundation of a robust electrical system that keeps everything running smoothly and safely. Today, we will focus on understanding and selecting the proper protective scheme and type of earthing for electrical systems. This is a crucial aspect because choosing the right protection method and earthing type ensures safety, reliability, and efficient operation of the electrical network. First, let's consider what protective schemes are all about. They are essentially strategies or systems designed to detect faults and disconnect the affected part of the system quickly. Proper protection minimizes damage and prevents hazards like electric shocks or fires. Next, the type of earthing we choose plays a vital role in fault management. Earthing provides a reference point for the system and helps in controlling voltage levels during faults. Different earthing methods, such as solid earthing, impedance earthing, or resonant earthing, are selected based on the system requirements and safety considerations. It's important to understand that the correct combination of protective schemes and earthing types not only enhances safety, but also improves system stability and reduces downtime. When selecting these, we need to analyze factors like system voltage, load conditions, and fault levels. In the context of our overall theme, designing safe and reliable electrical systems, this knowledge helps us make informed decisions that protect both equipment and personnel. So, always consider the specific characteristics of your system and consult standards and best practices when choosing protective schemes and earthing types. This slide doesn't contain enough information. That's why we're moving to the next slide. The objective of a protection scheme is to keep the power system stable. And we do this by isolating only the components that are under fault, while leaving as much of the network as possible in operation. This way, we ensure that the system remains reliable and efficient. The devices that are used to protect the power systems from faults are called protection devices. Now, understanding the significance and the need for these protective schemes is crucial, because they safeguard our infrastructure, prevent equipment damage, and help maintain continuous power supply. So, in essence, protection schemes are vital for both safety and system stability, connecting directly to our overall goal of a resilient and dependable power network. Let's take a closer look at the protection symbol. This symbol is really important because it quickly communicates that a product has been tested and meets certain safety standards. When you see this symbol, you can feel more confident that the product is designed to protect you in specific ways. It's a visual assurance that the item has gone through rigorous evaluation. Recognizing these symbols helps us make informed choices, especially when safety is a top priority. So, in the context of overall safety and quality, these symbols serve as a universal language, giving us peace of mind about the products we use every day. All right, let's take a closer look at some of the primary equipment and components in power systems. First, we have transformers. These are essential because they allow us to step up or step down voltage levels, depending on whether we need to transmit power over long distances or distribute it safely to consumers. Next, there are breakers. Their main role is to energize equipment and, importantly, to interrupt fault currents. This helps us isolate faulty equipment quickly, preventing damage and maintaining system stability. Then, we have insulators. These are vital for insulating equipment from ground and other phases, ensuring safety and proper operation within the system. Moving on, isolators, also known as switches, serve a crucial purpose. They provide a visible and permanent way to isolate primary equipment, especially for maintenance. They also help route power flow over specific buses, giving us control over the system's configuration. Finally, the bus. Think of it as a hub that allows multiple connections, or feeders, to be linked to the same power source, such as a transformer. This setup provides flexibility and reliability in how we distribute power across different parts of the system. Understanding these components helps us appreciate how each plays a role in maintaining a safe, efficient, and reliable power system. Let's take a closer look at the primary equipment and components essential for operating and maintaining electrical systems safely. First, grounding is fundamental. It provides a safe path for fault currents, helping us operate and maintain equipment without risking personnel or equipment damage. Next, arresters play a crucial role by protecting our primary equipment from sudden overvoltages, such as those caused by lightning strikes. They effectively divert these surges away from sensitive components. Switchgear is another key element. These are integrated components that allow us to switch, protect, meter, and control the flow of power within the system. They give us the flexibility and safety needed to manage electrical circuits efficiently. Reactors, on the other hand, serve to limit fault currents, especially in series configurations, or to compensate for charge currents in shunt setups, helping us control the system's reactive power and maintain stability. We also have voltage transformers, VT, and current transformers, CT, which are essential for measuring primary current and voltage. They scale down these high values to safer, manageable levels for protection and control systems, like P&C, metering, and SCADA. Lastly, regulators come into play. They help manage voltage, current, VARs, and phase angles, ensuring the system remains balanced and operates within desired parameters. All these components work together to ensure our electrical system runs safely, reliably, and efficiently. Understanding their roles helps us appreciate the complexity behind maintaining a stable power supply. There is no such thing as a fault-free system. That's an important point to remember because no matter how well designed or maintained a system is, faults can still occur. The safety of personnel should always be our top priority, so understanding the causes of faults helps us prevent accidents. Usually, faults happen because of insulation breakdown, which can be triggered by various reasons. For example, system overcurrent can cause insulation to weaken or fail. Overvoltage is another common cause, putting excessive stress on the insulation and making it more likely to break down. Lightning strikes are also a significant factor, especially in outdoor or exposed systems, leading to insulation failure. Now, you might wonder, why do we need protection systems at all? Well, the main reason is to safeguard both the equipment and the people working around it. Proper protection ensures that faults are detected quickly and isolated before they can cause serious damage or injury. This is a critical aspect of overall system reliability and safety. Remember, even though faults are inevitable, effective protection minimizes their impact, keeping our systems running smoothly and safely. Short circuits and other abnormal conditions are quite common in power systems. When these events happen, they often lead to a large flow of current, which we call heavy current. This heavy current can cause significant damage to the equipment in the system. Without proper protection, these faults can result in serious equipment failures, outages, or even safety hazards. That's why incorporating protective devices into the power system is so critical. They help detect these abnormal conditions quickly and disconnect the faulty section, preventing extensive damage. This slide underscores the importance of protection systems in maintaining the reliability and safety of our power systems. Let's take a closer look at some essential components of the protection system. First, we have the current and voltage transformers. These devices are crucial because they step down high currents and voltages to safer, measurable levels for protection and metering purposes. They help ensure that the system can be monitored accurately without exposing equipment or personnel to dangerous levels. Next, we come to relays. These are the intelligent parts of the protection system, acting as the decision makers. They detect abnormal conditions like faults and then send signals to trip circuit breakers, isolating the problem quickly to prevent damage or outages. Speaking of circuit breakers, these are the protective switches that automatically disconnect parts of the system when needed. They play a vital role in containing faults and maintaining system stability. Their quick operation is key to minimizing equipment damage and ensuring safety. Moving on, batteries provide backup power to the protection system. In case of main power failure, they keep essential protection devices operational, maintaining the reliability of the entire system. Fuses are simple yet effective safety devices that protect against overcurrent conditions. When a current exceeds a safe level, the fuse blows, breaking the circuit and preventing further damage. Finally, lightning arresters are installed to protect the system from surges caused by lightning strikes. They divert the high-voltage surges safely to the ground, safeguarding the equipment and maintaining system integrity. All these components work together seamlessly, forming an integrated protection system that ensures safety, reliability, and stability of the electrical network. Let's talk about current transformers. They typically consist of at least 2 secondary windings. The first winding is generally designed for measurement purposes, allowing us to accurately read current levels. The second winding, on the other hand, is used for protection, helping safeguard the system by providing reliable signals for protective devices. It's also important to note that the secondary windings of current transformers are almost always connected in a star or Y configuration. This setup is crucial for ensuring proper operation and safety in the system. Understanding these key points helps us see how current transformers play a vital role in both monitoring and protecting electrical systems, forming an essential part of overall system reliability and safety. All right, let's talk about voltage transformers. Typically, a voltage transformer consists of 2 windings. The first winding is connected in a star, which is also known as a Y connection. It's important to note that the star point must be earthed to ensure safety and stability in the system. The second winding, on the other hand, is connected as an open delta. This configuration is useful because it allows for flexibility and efficient voltage transformation without needing a complete delta or star connection on both sides. Understanding these configurations helps us see how voltage transformers adapt to different system requirements, ensuring accurate voltage measurement and protection in power systems. These design choices are fundamental to maintaining system stability and safety, which ties back to our overall theme of reliable power distribution. Let's talk about the main purpose of a relay. First, it isolates the controlling circuit from the controlled circuit. This means we can safely control high power or high voltage systems without risking damage to our control devices. For example, using a low voltage control signal to switch a high voltage system. Similarly, it allows us to control high current loads with a low current control circuit, which is much safer and more efficient. Overall, the key idea is that relays act as a safe bridge between different circuits, enabling us to control large or dangerous systems with small, manageable signals. This is essential in designing safe and reliable control systems. When a system failure occurs, it's crucial to detect it promptly and accurately. This allows us to quickly identify the faulted section and isolate it from the rest of the system, preventing the issue from spreading. By doing so, we can effectively mitigate the effects of failures after they happen, minimizing damage and downtime. Another key benefit of this approach is reducing the risk of fire or danger to personnel, which is vital in high-voltage environments. Protecting both people and equipment is always our top priority. This is where protective relays come in. They are essential tools that help us achieve these safety and reliability goals. Using protective relays ensures that faults are quickly identified and isolated, which ultimately enhances the overall safety and resilience of our systems. Now, let's take a closer look at the different types of circuit breakers, starting with the low-voltage circuit breaker. These are typically used in residential and commercial applications where the voltage levels are relatively low. They're designed to protect electrical circuits from overloads and short circuits, ensuring safety and reliability. Moving on, we have magnetic circuit breakers. These are a specific type of circuit breaker that use electromagnetic forces to trip the breaker when a fault occurs. They are fast-acting and highly reliable, making them ideal for protecting sensitive equipment. Next, we encounter medium-voltage circuit breakers. These are used in industrial settings and power distribution networks where the voltage levels are higher. Generally between 1 kV and 72.5 kV, they are crucial for managing larger loads and ensuring the stability of power systems. Finally, we have high-voltage circuit breakers, which are essential for transmission systems operating at very high voltages. Often above 72.5 kV, they play a vital role in maintaining the integrity of the entire power grid by safely interrupting very high power flows during faults. Overall, the common thread here is that circuit breakers, regardless of their voltage level, are fundamental components for protecting electrical systems, enhancing safety, and ensuring continuous power supply. Let's talk about circuit breakers. These are crucial safety devices in electrical systems. Their main role is to protect circuits from damage caused by overloads or short circuits. When the current exceeds a safe level, the circuit breaker automatically trips, cutting off the power supply. This prevents potential fires or damage to equipment. Think of it as a smart safety switch that responds instantly to abnormal conditions. It's important to understand that circuit breakers are not just for safety. They also help in maintaining the overall reliability of electrical systems. In the context of our presentation, circuit breakers are a key component in ensuring safe and efficient operations. They act as the first line of defense, safeguarding both people and machinery. Recognizing their function helps us appreciate the importance of proper electrical system design and maintenance. Battery banks are called as backbone of protection system. They play a crucial role in ensuring the reliability and safety of the entire power system. In case of a power failure or emergency, these batteries provide the necessary backup power to keep critical systems running. Essentially, they serve as an emergency power source, stepping in when the main supply is disrupted. This is why they are so vital. They support the overall stability and protection of the system. So, when we talk about the protection system, remember that the battery bank is its backbone, ensuring continuous operation even under unforeseen conditions. Fuses are carefully selected components designed to handle the normal current flow in a circuit, but they are also crucial for protecting the system during excessive current conditions. When the current exceeds a certain limit, the fuse acts as a safeguard by breaking the circuit, but it does so only for short periods. This quick response prevents damage to other, more sensitive parts of the system. It's important to note that fuses are used specifically to protect low voltage or low current devices. If the current becomes too high, the fuse will blow, effectively disconnecting the circuit and preventing damage or potential hazards. So, in essence, fuses are vital safety devices that ensure our electrical systems operate smoothly under normal conditions and are protected during overloads. They're simple yet incredibly effective in maintaining circuit integrity and safety. A lightning arrestor is a device used on electrical power systems to protect the insulation from the damaging effects of lightning strikes. Essentially, its main role is to prevent lightning from causing serious damage to the equipment and infrastructure. All lightning arrestors are earthed, meaning they are connected directly to the ground. This grounding is crucial because it provides a safe path for the lightning current to flow into the earth, rather than passing through and damaging the system. So, in the context of our overall theme of system protection, lightning arrestors act as a vital safeguard against the unpredictable and powerful nature of lightning, helping ensure continuous and safe operation of electrical networks. Switchgear is essentially a combination of switches, fuses, or circuit breakers, or sometimes a mix of these components. Its main purpose is to control, protect, and isolate electrical equipment within a system. Think of it as the control center that manages the flow of electricity. It is used to de-energize equipment when necessary, such as during maintenance or repairs, ensuring safety for personnel and equipment. Additionally, switchgear is crucial for clearing faults. If there's a short circuit or overload, it quickly isolates the problem to prevent damage or outages. In the broader context of electrical systems, switchgear plays a vital role in maintaining the safety, reliability, and efficiency of power distribution. It's a key component that helps us manage electrical power responsibly and effectively. Today, I want to talk about the different elements of switchgear, which are crucial components in electrical systems. When we look at switchgear, we're essentially examining the various parts that work together to control, protect, and isolate electrical equipment. These elements are vital for ensuring safety and reliability in power distribution. First, we have the circuit breaker, which is designed to automatically disconnect a circuit in case of overload or short circuit. It acts as a safeguard to prevent damage to the system and ensure safety. Next, there are disconnect switches, or isolators, which allow us to manually open or close circuits for maintenance or safety reasons. They provide a visible break in the circuit, making it clear that the section is de-energized. Then we have fuses, which are simple yet effective. They protect the system by melting when excessive current flows, thereby disconnecting the circuit. Fuses are often used in smaller or less critical applications. Another important element is the relay, which acts as an automatic switch that responds to electrical signals. It can activate or deactivate other components based on certain conditions, providing automation and control. Finally, we can't forget the busbars. These are conductive bars that serve as the main connection points for incoming and outgoing circuits within the switchgear. They distribute power efficiently to different parts of the system. All these elements work together seamlessly to ensure that our electrical systems are safe, reliable, and easy to maintain. Understanding each component's role helps us appreciate the complexity and importance of switchgear in power distribution. Now, let's take a closer look at the operation modes of these protective devices. First, we have automatic and manual operation types. For example, devices like circuit breakers, MCBs, and MCCBs are designed to operate automatically to protect the system without human intervention. They sense faults and trip automatically to isolate the problem quickly. On the other hand, fuses are a bit different. They are only manually activated or operated. You need to replace or reset them after they blow, so they require human action to restore the circuit. Then we have isolators and load break switches, or LBS. These are primarily used for isolating parts of the circuit for maintenance or safety purposes. They are usually operated manually and are not meant to trip automatically during faults. Understanding these categories helps us choose the right protective device for the right application, ensuring safety and reliability in the electrical system. Remember, the key is matching the device's operation mode to the specific needs of the circuit and its protection requirements. Let's take a look at the different categories of switchgear based on voltage levels, starting with low-voltage switchgear, which typically handles up to 11 kilovolts. These are commonly used in residential and commercial applications, providing safe and reliable distribution of electricity. Moving up, we have medium-voltage switchgear, capable of handling up to 66 kilovolts. These are essential for industrial plants and distribution networks, helping to manage higher power demands safely. Next is high-voltage switchgear, designed for voltages up to 400 kilovolts. These are crucial in transmission systems, where high voltages are used to efficiently transfer electricity over long distances. Then, we have extra high-voltage switchgear, which can handle up to 765 kilovolts. These are typically found in large-scale transmission networks, supporting bulk power transfer across regions. Lastly, there's HVDC switchgear, used in high-voltage direct current systems. These are vital for specialized applications like cross-border power exchanges and undersea cables, where traditional alternating current systems might not be as effective. Overall, understanding these categories helps us appreciate how switchgear is tailored to different voltage requirements, ensuring safe, efficient, and reliable power distribution across various levels of the grid. Let's take a closer look at the various factors that can cause faults in power systems. First, weather conditions play a significant role. For example, lightning strikes can directly damage equipment, while heavy rains and strong winds can lead to physical stresses on the lines. Salt deposition on overhead lines and conductors, as well as snow and ice accumulation, can also disrupt the smooth flow of electricity and increase the risk of faults. Next, equipment failures are another major cause. Components like generators, motors, transformers, reactors, and switching devices can malfunction over time. Issues such as aging, insulation failure of cables, or winding faults often result in short-circuit faults, which can severely impact the system's stability. Human errors, although sometimes less obvious, are equally critical. Mistakes like selecting equipment with improper ratings, forgetting to remove metallic or electrical conducting parts after maintenance, or switching circuits while they are under service can all lead to faults. These errors highlight the importance of careful procedures and vigilance. Finally, fires and smoke also contribute to faults. Ionization of the air caused by smoke particles around overhead lines can create sparks, leading to flashovers. Such flashovers can cause insulators to lose their insulating properties, especially under high-voltage conditions, resulting in system failures. Understanding these causes, weather, equipment failures, human errors, and fire-related issues, is essential. They all tie back to the overall goal of maintaining a reliable and safe power system. Each factor underscores the importance of proper design, maintenance, and operational practices to minimize faults and ensure continuous power supply. Now, let's talk about symmetrical faults. These occur when all three phases are shorted to each other and also to ground simultaneously. This type of fault is quite rare, but it is important to understand because when it does happen, it is the most severe of all fault types. The reason for this is that the fault current in this case reaches its maximum possible value, which can cause significant damage to the system components. Moving on to unsymmetrical faults, these involve only one or two phases instead of all three. There are different types of unsymmetrical faults to be aware of. The first is the line-to-ground fault, or LG fault, where a single phase is shorted to ground. Then we have the line-to-line fault, or LL fault, which involves a short circuit between two phases. Lastly, there's the line-to-ground fault, or LLG fault, where two phases are shorted together and both are grounded. Understanding these different fault types helps us better analyze system behavior and improve protection strategies. Recognizing whether a fault is symmetrical or unsymmetrical allows us to respond appropriately and ensure system stability and safety. Now, let's take a closer look at the fault types associated with shunt configurations. When we talk about faults in shunt systems, we're essentially referring to unintended electrical paths that can cause issues within the network. These faults can vary, but understanding the common types helps us better diagnose and address problems. The most typical faults include phase-to-ground faults, phase-to-phase faults, and three-phase faults. Phase-to-ground faults happen when a conductor comes into contact with the ground or a grounded object, which can lead to overcurrent and potential equipment damage. Phase-to-phase faults involve two conductors shorting together, creating a direct path between phases, and often resulting in a sudden surge of current. Three-phase faults are the most severe, involving all three conductors shorting together, which can cause significant system disturbances. Recognizing these fault types is crucial because each has different implications for system stability and protection strategies. By understanding the nature of these faults, we can implement more effective protective measures and maintain the reliability of our power systems. Throughout the presentation, we've emphasized the importance of accurate fault detection and response, especially in shunt systems where quick action can prevent widespread outages. This slide doesn't contain enough information. That's why we're moving to the next slide. This slide doesn't contain enough information. That's why we're moving to the next slide. Let's take a closer look at the frequency of different types of faults. Here, we see how often each fault type occurs, which is essential for understanding where the most common issues arise. Recognizing these patterns helps us prioritize our maintenance and intervention efforts. For example, if certain faults appear more frequently, we can focus on preventive measures to reduce their occurrence. This slide underscores the importance of data-driven decision-making in maintaining system reliability. By identifying the most prevalent faults, we can improve overall performance and minimize downtime. Remember, understanding fault frequency is a vital step in developing effective maintenance strategies and ensuring system resilience. Let's take a closer look at the frequency of fault occurrence. This slide highlights how often faults happen in our system, which is crucial for understanding reliability and planning maintenance. What we see here is that faults don't occur randomly. Some components or processes are more prone to failures than others. Recognizing these patterns helps us prioritize areas for improvement and focus our resources effectively. By analyzing the frequency data, we can identify components that frequently fail and develop strategies to mitigate these issues, ultimately reducing downtime and increasing overall system stability. Connecting this to our broader theme, understanding fault frequency is essential for designing more robust systems and ensuring continuous operation, which is vital in today's fast-paced, technology-driven environment. This slide doesn't contain enough information. That's why we're moving to the next slide.